capacity.
Could you close the door, please? Thank you. Please, could you close the door? Thank you very much. Okay, so let's start by some definition. Are you ready?
Yes.
Okay, so I am going to present you what is a capacitor. Okay, by definition, a capacitor is an ensemble, a set of two conductors, okay, connected with different charges. So a capacitor, can you read me here? Okay, is a set of two isolated conductors with opposite charge. So plus minus Q and plus Q. Okay? So a capacitor is basically a device to store some electric energy. Okay, so here is here is a conductor, and here is another one. Okay, and on one conductor there is a charge plus Q, and on the other one there are minus charge Q. Okay, and of course in between the two conductors there is an electric field going from the charge plus to the charge minus. Okay? Okay. So, of course, there are very more simple capacitors. The best one is, for example, plate. So for example, you can have a cylinder like this, and you have two okay. And if you look at above, you have something like this. So this is a capacitor. So this is a cylinder capacitor. Okay. And of course, simple capacitor is composed of two plane conductors. Okay. Like this. And we can also draw them like this. And of course, in that situation, the electric field is like this, sometimes like this. Okay. The symbol of a capacitor is like this. So two parallel bars like this. Okay, so let's see some property of this. Okay, so because the two elements of a capacitor are conductors, that means that all the points of one plate has the potential, the same potential. And the other one, of course, is V1. So, plates of a conductor are all points of each plate of a conductor, of a capacitor, have the same potential. So we are going to note them V plus and V1. We define, okay, so V plus here and V1, okay, here. Okay, we note, sorry, so usually delta V is the difference between V plus minus V1, but sometimes we note only V instead of delta V. Okay, so this is only the notation, but remember that V is in fact a difference of potential. Okay. Okay. A capacitor is characterized by its capacitance which is by definition Q over V. Okay? So this is one intrinsic characterization of the capacitance. And as I will show you, see only on its geometry. We will see that later. And just to mention mention the unit, of course. The unit of the capacitance, as you can see, it's Coulomb over volt, and we also call it Farad, and not them F. Okay, so at the beginning, a capacitor is only an ensemble of two conductors, so the conductors are not charged. So how can we charge a capacitor? We just have to connect the capacitor to a battery. Okay? So I'm going to draw. So this is a battery. This. Okay. And this is the capacitor. And here is what we call a switch. Okay, so here is the battery B, and we will see that the battery, as you may know, has always a positive pole and a negative pole, and this positive is here. And we are going to connect by wires the positive pole to one of the conductor of the capacitor, then to the switch. This is switch S. And this is capacitor C. And then we are after connect the switch to the battery. Okay, so of course you can understand that if we switch on here the switch, then the current, we will see that we'll be able to run in the circuit, and then at the end we have the potential here V plus, and of course here V minus. Okay, so this is how we can charge a capacitor. Okay, so this drawing here is quite long to draw. Okay, so this will be later on. Now I'm going to draw this kind of circuit like this. So this is B, this is C, this is F, this is B plus, this is V1. Okay? So now, when you will see that, okay, this is a scheme representing this kind of circuit. Okay? So let me Oh yes, okay. You need time, right?
Yes. It's okay.
Okay, so I'm going to write what I've just said now. If you switch on, the capacitor will be charged, but if after disconnecting, after switching off the switch, the capacitor will remain charged. Okay? So can I turn the page?
Okay.
Of course, the capacitor will charge until V equal. Okay. Here, when you switch on the switch, of course, the two plates of the conductors of the capacitor, sorry, will have the same potential as the battery. Okay. Okay. It's okay for this? It's okay for definition? Yes, please.
So a few minutes ago, I hear that if I switch off the switch, so the capacitor is still charged. So how can it charge?
Because when you switch off the switch, the current cannot circulate in the circuit now. Okay, so there is no charge moving in the circuit, so the capacitor remains charged. Okay. Any other question? Okay. So now, one question is how to calculate the capacitance. As I said before, it's not obvious, but C, the capacitance of a capacitor, only depends on its geometry. So we are going to see that now in few examples. Okay? Okay, so here is the general method. So the first thing is to identify the location of the charge. So where are the charges? Then, after that, you will have to calculate the electric field between the two conductors, and for this I recommend you to use the Gauss law. Okay. Then after that you have to calculate the V. Okay. Using the definition. Okay. So this is the general method, and now we are going to apply it all together. Are you ready? Okay, so let's start by the simplest capacitor. It's the parallel plate capacitor. Sorry. So here is the drawing again. Okay, so imagine that the charge plus here and here the minus charge. Okay. So here are the G is the distance between the two conductors, and here I didn't say that, but A is the surface area of the plate. Okay? So as you may know, the electric field between the two conductors are going from here and are perpendicular to the plates. Okay? E Okay, so morning exercise. How are you going to calculate E?
E equal F over Q.
Equal F over Q, but we do not know F here. Again, read again. In the general method, we are going to calculate the electric field here with the Gauss law. You remember?
Yes.
Okay, so what you are going to see to consider is this Gauss law. So something like this. Here, 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 here. Okay. So with the Gauss law, you need to define a closed surface. Okay, so something like this. You see what I mean? Here. Just consider this Gauss surface. Okay, so I'm going to let's see here like this. This is the Gauss surface, okay? Can you see it? Okay, so now it's like a parallelepiped. So the flux, you remember the Gauss law? So the Gauss law said that the charge inside, or the net charge, is equal to epsilon 0 the flux of the electric field through the surface of the gauze surface. Okay, so remember that here when the electric field is parallel to the surface, E dot ds, okay, ds is, remember that ds is like this. Oh, sorry. No, so it's dA, sorry, not ds. dA, sorry. And okay? So the vector dA are perpendicular to the surface. Do you remember this?
Yeah.
Yes? Okay, so if E is parallel to the side of the surface, the E dot dA is equal to 0. Okay? So here, and of course, there is no electric field here. Here, I'm going to put it E equals 0. But here, E is what you are looking for. Okay, so at the end, the Q net is equal to simply E dot the surface of the plate. Do you understand this? And what is Q net? Q net is simply the surface charge density here, meaning the number of charge divided by the surface times the surface. Are you agree with that? Okay, so at the end, you can see that E is simply equal to sigma to epsilon 0. So the field, the electric field between two parallel plates is simply sigma, the charge density of the plates, divided by the permittivity constant epsilon 0. Is that clear? Okay, so now we can calculate the difference of potential. So V plus minus V minus, okay, V is this is the minus, you have to remember this, the integration between this point, let's say A or here, let's say E to G, okay, so A to G time E, the small displacement between A and G here. Yes. Oh no, this is not D plus, but sorry, because if we are going to E I to J, sorry, it's V minus, of course, V minus is here, V plus is here, so it's different here. Let's say minus V equal this. Okay, so E scalar ds is only at the end E times D, because the two vectors are parallel. Okay, so that means that V equal EG. the difference, again, the difference of electric potential between the two plates is simply Eg. Okay? So at the end, the capacitor is equal to Q over V. Okay? And from here you can see that Q is epsilon 0 EA divided by V, which is equal to Eg. And see, at the end we have just epsilon 0 A over T. So as I said you, the capacitance of parallel plates conductors only depends on the geometry of the capacitor. Okay? It does not depend on V or E. Yes, you have any question? Sure?
So this is a sigma.
Yes?
This is a sigma.
Yes, sigma. Sigma is the density of charge.
Thank you.
Okay, more complicated. Any question? It's okay? Okay, so let's calculate the capacitance of a cylindric capacitor. So, if we draw a cross section of the capacitor, we have this, okay? This is a cylindric. And inside we have this. Okay? So, we can decide that this one is plus Q and this one is minus Q, whatever. Okay? So in that case, the electric field is radial by geometry. Okay, E. Okay, so of course the radius yes, R, sorry. Oh yeah, no. In that case, sorry, the geometry of the cylinder is, of course, is its length, which is perpendicular to the plane here, and A is the radius of the inside cylinder, and B is here. Okay. So, okay, for the plain capacitor, maybe you could learn by heart the result. Okay? But for the cylinder, after that, it's not necessary to learn it. Okay? Just learn the method again. Okay, so we have identified where the charge. We are going to use the Gauss law again to calculate the field E, okay? So, usually we consider the Gauss law here, inside, somewhere here, okay? Gauss, your face. Of course, it's a cylinder. Can you imagine that? Yes? Okay, so now we are going to apply the Gauss law again. So according to the Gauss law, the flux of this electric field around the surface of the cylinder here is equal to Q net. So Q net equal F0. So here, what is the result? It's the surface, the lateral surface, right, of the cylinder. So it's 2p, let's say R, L. Are you agree with that? Yes? The surface of the Gauss surface is, let's say it has a radius R, okay, of course, here. Okay, so 2pr times L is the surface of the cylinder. Are you agree with that? Yes? Yes, okay? So, and Q net, what is the Q net? Is okay, let's keep Q. Q and Q equal Q net. Okay? Because all the charge are here. So at the end, E equal Q over 2p R L. Yes? Yes, epsilon 0. Thank you very much. Yes, epsilon 0 here. Thank you. Okay, so now, last step of the method, we need to calculate the difference of potential. Okay? So if we are going to from here to here, again, EG, it's not the same of EG here. The integral of EG is scalar ds equal VG yes, is VG minus VG. So VG is equal to, so this is minus V. Okay, so V equal, so you can see that the field E is depending on the position inside the cylinder. So it's equal to the, when E is equal, the radius is A, and at point G, the radius is G. And we have Q over 2 pi epsilon 0 L, so ds dr over L. Oh, this is minus, sorry. Yeah. Okay, so, and this is of course the integral of 1 over R is, what is the integral of 1 over R? Is logarithm ln. Yes? Good. Yes. So this is minus Q over 2p epsilon 0 L ln of B over A. Okay. course, it's also it's okay? So at the end, C, sorry. So at the end, the C is equal to Q over V, and if you did this, you obtain 2 pi epsilon 0, the length, okay, divided by, sorry, I made a mistake, a sign mistake somewhere. Oh no, okay, there's 2 signs here, sorry. Okay, so again, the capacitance of a cylinder capacitor only depend on the geometry L, B, and A of the capacitor. Are you convinced now? Okay, so let's also just because this figure could be also the figure of a capacitor made of 2 spheres. Okay? So now we can talk about spherical same figure. Okay? But what is changing is the surface, of course, of the Gauss law and the Gauss surface. Okay, so we can say that Q, now it's epsilon 0, EA, E, let's say, time. So now let's say the surface, the Gauss law, is not 2πr time L, but what is the surface of a sphere? For PR2, right? Instead of 2PRL. Okay? So now the field E is equal to Q over 4P epsilon 0 R2. And this is also a field depending on R. And now, for the potential, again, so instead of having this, we can say we have to okay. And of course, the primitive of the integral of the function 1 over R2 is 1 over R, exactly. So we have 1 over R, and of course, yes, but minus, but, okay, if you want, but I have 1 over B, okay, good. Oh, you're right. You follow me, I'm happy. Okay, so of course at the end C is equal to Q over V, and this time we obtain 4P epsilon 0 and again we have a capacitance which only depends on the geometry of the capacitor. Okay, so just a very important remark, but not very important, but in this case, if the B tend to the infinity, okay? Imagine you have a metal sphere and around another metal surface, okay? This is a capacitor. But now imagine that the outside sphere is larger until the infinity. Okay? So in that case, the remained inside sphere constitute a capacitor. It's a case of a capacitor composed of only one metal, one conductor instead of two, okay? But in fact, we need to imagine that the second conductor is it's very big, okay? So if B equal tend to the infinity, then we obtain a capacitor made of one, sorry?
The paper is not fit.
Oh, sorry. Of radius A, made of one conductor of A. And of course, in that case, C, if B is going to infinity, you have 4P epsilon 0 A. Okay. So now, you have any question? It's okay?
Yes.
Yes?
So at this, this formula, where's the Q?
There is no more Q here, because see, if you from the previous equation,
Yes.
if you make Q over V, there is no Q. Okay?
Okay.
So again, the capacitance of a capacitor only depends on the geometry. Okay? It's an intrinsic characteristic property. Any question? Any other question? Okay, so now let's see what happens if we have several capacitors in parallel and in series. Okay, so imagine that we have a battery connected to a first capacitor, okay, and then a second capacitor, and then a third capacitor. Okay? So this is V plus, this is V minus. Okay, so this is a battery, this is C1, C2, C3. So here, can you read me? No? C1, C2, C3.
Yes.
Okay? And B is a battery. Okay? here C1, C2, C3 are said to be in parallel. Okay? So why? Because here what is important is the potential of this point is the same. Okay, because these 4 points are connected by wires. Okay, so they need to be at the same potential. And this point have the same potential. Okay? So they have so for each capacitance V is the same. Is equal. Okay, but not necessarily the charge. Okay, the charge, let's say, here. Let's see that after. The charge of each capacitor is for R, Q1 is Q1, Q2, and Q3. Okay? So, the total charge, so imagine here you have Q1, you have Q1 here, Q2 here, and Q3 here. Okay? So, these 3 capacitors are in parallel, are equivalent to this. With Q of the 3 capacitors is Q equal Q1 plus Q2 plus Q3. Okay? And so okay, so now we can say that Q, of course, Q1 by definition is, you can see that it's C1 V, Q2 is C2 V, and Q3 is C3 V. Yes? Okay, for each Q1 is equal to C1V, Q2 is equal to C2V, and Q3 is equal to C3V. Okay? So of course this is C1 plus C2 plus C3 times V. Okay, so we can say that three capacitors in parallel are equivalent to only one capacitor, okay, with the capacitance C with, so let's say this, 3 capacitors in parallel. Of course, it's not limited to 3. Is are equivalent to 1 capacitor of capacitance C. Okay? So if you want to store more energy, more electric energy, you need to put several capacitors in parallel. Okay? Because again, the capacitance is the capability to store some electric energy. Okay. It's okay?
30 seconds.
So this is in parallel. Okay, can we continue? Yes?
Yes.
Okay, so now in series, it's the... So now we have, like this, 3 So we have a battery, C1, C2, C3. So now you can see that the connection is different. This is a series connection. Okay, so what we have this is V plus, V minus. But now, the difference of potential of the 3 capacitor is different. Okay? So we just know that here we have V plus, and here we have V minus. But in between we do not know. Okay? But we know here in that case that if we have the charge Q here, then necessarily you have the charge minus Q here. And necessarily because here you have the circuit is neutral. You have minus Q plus Q minus Q. So in series, the charge of all the capacitors is the same. Okay? Of all capacitors is the same. Okay, so here let's note that, for example, this is V2 and this is V3. Okay? and V1 of course is equal to V plus. So let's say V. We have, if we, of course we will see that the sum of this potential is equal to V plus minus V1. Okay, so we can say that V plus minus V1, of course, is equal to V plus minus V2 plus V2 minus V3 plus V3 minus V minus. Are you agree with that? And then each so V plus minus V, and then we are going to replace this. This is Q. So V is equal to Q over C. Q over C1 plus Q over C2 plus Q over C3. Okay, so that means that V equal Q 1 over C1 plus 1 over C2 plus 1 over C3. And this is, we can see, we thus can see that this circuit, this is equivalent to this. Okay, so in other words, three capacitors in series are equivalent to one capacitor with the capacitance one over C equivalent equal. Okay, so if you put three capacitors in series, you do not necessarily increase the capacity of store energy or store, okay? It will depend on the number. So three capacitors in series are more complicated. It's okay for that? Okay, so now let's see what is the energy stored in a capacitor. Do you have any question? It's okay? So what is the energy stored in a capacitor? So let's see that again. Okay, so basically, a battery is something which provides energy to the charge. Yes? Okay, so it's like a working. Imagine that I replace the battery by a man, by me, okay? And if I want to charge these two things, I'm going to put a charge here and then put again. Okay? And this is at time t equals 0, there is no difference in charge. Okay? But now I'm going to take, let's say, one charge here. Imagine I'm going to take one charge here. Let's say one charge. I'm going to throw it here, and I'm going to put here. You understand? Okay, so I'm going to take one charge here and I'm going to pull it from here to here. Okay? And then at the end, of course, I have this. At the end, we have plus Q here. Okay? And of course, I will have minus Q here because the conductor is neutral. Okay? So the work of course, the energy required to move a charge from one plate to the other one of the capacitor is W. So what is the work at the end? We have, of course, minus plus. It's, as I said before in the previous chapter, is the energy of the charge at the potential V plus minus the energy of the charge at the potential V1. Yes, I'm sorry. Yes, I'm just being more clear. This is a dq, a small charge, okay? I'm going to put them. Okay, so again, I repeat because imagine that I'm moving a charge dq from here to here. So at the end we have minus dq plus dq. So here it's a dq. And of course here it's a small work. Okay. Do you understand? It's okay? So of course, this is at any time t. Sorry, it's not necessarily time t, but this at the time t V plus minus V1 is equal to the charge over the capacity, the capacitance. So W is equal to Q dQ over C. Okay, so the total work, of course, is the sum of all this work and is equal to Q, and this is only Q2. Okay. Oh, sorry. Sorry about this. So the energy store, so conclusion, the energy stored in a capacitor is, so we can say U now because it's, okay, it's Q2 over 2C. Of course, you can replace the Q with the V and you have CV2 over 2. Do you have any question? It's okay? Okay, so I'm not sure if I have time, so I will switch this. At what time should I finish?
12 over 10.
Okay. Okay, we'll be short, so okay, let's go. I think. Okay, so now we have seen. I'm going to switch some part because we do not have time, but it's not okay. It's okay, can we continue?
Yes.
Okay, so let's move to the next chapter, which is chapter 26. So we are now going to see what is the electric current and resistance. Okay, so first part, definition about the current rate. Okay, so let's remind me that in a conductor, electrons, which are the elementary charge, are free to move. Okay, so let's see. Of course, yes. So let's consider a wire here. A conductor wire. Okay. And so, as I said before, electrons are free to move in the conductor wires. Okay? Of course, when electrons move in one direction, okay, it is equivalent to the fact that, sorry, I'm going to, that opposite charge are moving in the other direction, okay? Are you agree with that? Okay, so when electrons are moving like this, it's equivalent that what we call the positron, which is the opposite of the electron, are moving in the other side. Okay? So now let's see if we consider here a section. This is a section of the wire, okay. But by definition, so the current, so of course I didn't mention, but when charge are moving in a conductor, it makes a current, okay? The current is, I didn't, okay, I'm going to read it. A current is an ensemble of moving charge. In a conductor. Okay. The rate current, by definition, the current rate is the amount of charge which cross a section of the conductor of the wire during a time, the amount of charge dq during a time per unit time unit. So basically the definition is the current E is equal to the amount of charge which goes through the section. Okay? dq is the number of charge which cross the section, and you have to divide it by dt to have the time unit. It's okay? Okay, just some unit. So the unit of a current rate is coulomb of a second, and this is ampere. It is not A. Okay, and just by convention, it's only a convention, by convention, current is represented with an arrow. Okay, So oriented in the supposed, because we do not really know, direction of positive charge. Okay, so here the current will be like this. And if we know that the direction is going like this. Okay, I repeat, by convention, the current is represented with an arrow which is oriented to the supposed direction of positive charge. Any question? No? Okay. So just also, let's say, what happened at the junction? Imagine that we have a wire here, we have a junction here, and imagine that, yes? Sorry. Thank you. Okay, so we have a junction. Imagine that we have a current here called V1, and here we have E2, and here we have E3. Because the number of charge is conserved in the nature, okay? So there is no creation or destruction of charge in the nature because of the nature. So because of the conservation of the charge, we necessarily have E1 equal E2 plus E3. Okay? Okay, so now, any question? It's okay for the definition? So now, let's talk about resistivity and resistance of material. Resistance and resistivity of materials. So we can make an experiment. If we apply a potential between, let's consider two materials. This is, for example, copper. And here is the same geometry, but glass, some glass. And if you apply the same potential, V. So, in fact, we can observe a current going here, okay, also here, E, and here also we observe we observe the current in the copper is much more higher than the current in the glass. Okay? So that means that some material, let's say, are opposed to the moving of the electrons. Okay? So exhibit okay, they prevent the motion of the charge inside. Okay? By definition, the resistance of a material of a conductor, let's say, but still the copper and the glass are conductor, okay? But we can say that they are good conductor or bad conductor, okay? Okay, by definition, the resistance of a conductor is equal to the difference of potential at the two ends divided by the resistance by the current I. Okay, so let's see some. Can I turn the page?
1 more minute.
Okay.
Okay, you can turn it.
Okay, so of course, the unit of R, you can see that it's volt over ampere, and this is ohm. And we note it like with an omega. Okay. So let's remind you, a bad conductor has a large resistance, and of course a good conductor has a low resistance. Okay? Oh yes, the symbol of a resistance is like this. And of course, you can guess that a wire of copper is a very good conductor, and the resistance is very close to zero. Okay? Okay, so I'm not going to do this. Okay. Any question? It's okay? Yes? No? Okay, so now let's talk about the Ohm's law, which is not really a law, but we will see what it is. Okay, so if we make this experiment, so again, it's the same experiment. We have an object, a conductor, some wire. Okay, so V. So, and this is, so now I'm going to put R. Okay. And so, and we, of course, can measure, I will see, the resistance, the current E through R. Okay? But now V is, let's say, can move, is a variable, sorry. Okay? So if we measure the current as a function of V, okay, sometimes we will see that the current is proportional to the density. But sometimes we will not see that. For example, we can see that. Okay, so depending of the response of this experiment, we can see that a resistance, a conductor, this is R is a conductor, okay? It's or it's a resistance. Conductor. Okay, we can say that a resistance resistant conductor obey the Ohm law if its resistance meaning E is linear to V. Okay? So we say that a conductor, a material with a certain resistance, we say that this conductor obeys to the law of Ohm, or the Ohm's law, if the resistance R is independent of the potential, meaning that the intensity, the current rate is linear to the potential. So this is okay. In that case, we can see that this one obeys And this one do not obey Ohm's law. Okay, you understand? This is not really a law. This is rather a rule. Okay, this is a criteria. Okay, we have some materials which can obey this rule, and some other materials we do not obey this rule. Okay? And of course, in that case, we have the difference of potential is directly equal to no, it's always the case. Okay, I mean it's not sorry. This is always the case. Okay. So now let's talk about power. Power of love. No, not power of love, electric power only. Okay, so imagine this. Let's consider again a battery connected to, let's say, any device. So, at the equilibrium, the battery maintains again the potential here, V plus, and the potential V1. Okay? This is at the equilibrium. Okay. Okay, to maintain the difference of potential, a battery have to move an amount of charge from A to B. Okay, so let's say we have A here, and here B. So let's say at equilibrium, the battery is maintaining the potential difference B plus 2. That means that necessarily, so that the battery maintains an electric current in the circuit. Okay, so this means that you have this necessary okay, because if the battery does not maintain this current, so necessarily the charge, the positive charge, will move to the negative potential, and there is no more potential. Okay. So let's now try to calculate, to estimate the energy necessary to maintain this current, okay, through the circuit, okay, in the circuit. So during, let's say, during a time dt, okay, the battery makes moving a charge dq from A to B. Okay, so no, A is here. Okay, so that's not the. Let's say A is here. Oh, it's not here. Do you understand what I mean? Okay, so if there is no current, okay, the charge which are here, the positive charge which are here, will move to V minus. Okay? So there is no more V plus and V minus at the end. Okay? So to maintain the difference of potential V plus and V1, the battery need to add a lot of charge to here and to take a lot of charge from here. You understand? During let's say, okay. And of course, this by definition dq equal E dt. Okay. And the potential energy required in the yes. So the potential energy associated to this moving is, of course, we have du equal dq minus dqb. So that means that the battery need to transfer the energy, let's say E battery equal minus du equal dqb. And this is energy. And because it do it as during a certain time, so we say that the power, electric power of the battery is P equal, oh yes, this is P, dq V over dt. So P equal E V. And let's say the units of the power is volt times ampere, which is what? Okay, I'll repeat. When you have this kind of circuit, okay, the battery, the role of the battery, the function of the battery is to add charge on one side and to take charge on the other side, okay? And to do it, the battery needs to spend some energy, okay? And as I said before, so if we consider the charge moving to take place and moving from here, you have to spend the energy dq times v, and so the battery has to provide the energy dTV, and that's equivalent to provide the power dB over dt, and this is equal to V over V times the current E. Okay? What time is it?
12:10.
Oh, sorry. Okay. Okay, so next time I will have to finish the electricity part, and also need to start the magnetism part. So I am a little bit late, but it's okay. Okay?
Okay.
So good weekend. Thank you.